All right, let's go ahead and get started. So, good afternoon, everyone. My name is Jeff Hare, and I am a co-founder and chief experience officer at Trifacta Incorporated. It's also, I have a side job alongside my work as a professor of computer science at the University of Washington, and prior to that, I was actually an assistant professor of CS over at Stanford. And kind of what unifies my activities in all of these different, different jobs is really strong interest in the topic of interactive data analysis. So obviously in many of the different sessions and discussions here at Hadoop Summit, we're thinking about how do we build better, scalable, efficient systems for data processing. And what I want to think about is how do we make that more accessible to a larger audience? What are the types of analysis tasks people want to do? How do we support them? And what kind of implications does it have for the kinds of systems we build, not just at the UI level, but also trickling all the way down into the underlying data processing systems. And we take a lot of inspiration for this. A lot of our interest in this topic and the work we do at Trifacta comes from the experiences we have directly working with data ourselves. But we also take inspiration from some of our heroes. And for me, one of those heroes is the statistician John W. Tukey, who's probably known to many of you. He's certainly a giant in the field of statistics in the 20th century. Within computer science, he also contributed such things as being a co-inventor of the fast Fourier transform. And he also popularized the notion of exploratory data analysis. So what are the ways that we get to know a data set, understand what modeling assumptions may hold, and also identify errors, anomalies, and patterns prior to engaging in analysis further. And in an article he wrote almost 50 years ago with his partner Martin Wilk, he had some really interesting comments that I think still have a lot of resonance today. So first off, Tukey wrote, 4 major influences act on data analysis today. 1, the formal theories of statistics. 2, accelerating developments in computers and display devices. 3, the challenge in many fields of more and larger bodies of data. And 4, the emphasis on quantification in a wider variety of disciplines. So already we can see that the 1960s was a very, very different time from today. So moving on, he goes on to write, while some of the influences of statistical theory on data analysis have been helpful, others have not. He says, exposure, the effect of laying open of the data to display the unanticipated, is to us a major portion of data analysis. Formal statistics have given almost no guidance to exposure, and indeed it is not clear how the informality and flexibility appropriate to the exploratory character of exposure can be fitted into any of the structures of formal statistics so far proposed. He then concludes that nothing, not the careful logic of mathematics, not statistical models and theories, not the awesome arithmetic power of modern computers, nothing here can substitute for the flexibility of the informed human mind. And so accordingly, both approaches and techniques need to be structured so as to facilitate human involvement and intervention. And so what he's doing in putting this is obviously not trying to put down the computational power, scalable systems, or statistics. Indeed, he was an advocate of all of these things, but rather understanding how they can be best marshaled to serve the needs of data analysis, which is actually a wide-ranging process. It's not simply the act of fitting a statistical model, but rather, from my own standpoint, a lot of my work is focused on visualization, but that too is just one component in a much larger process that we're all engaged in trying to help support. Everything from how do we acquire and discover data, how do we engage in cleaning and integration, really getting data ready for subsequent analysis tasks, understanding data, structures, anomalies, et cetera, through visualization, then moving through processes of modeling, prediction, then reporting and disseminating results. And it would be lovely if in practice the process works something like this as we move from one stage to another in a waterfall process. As we all know by having dealt with data and trying to do real-world analyses, in practice it looks something much more like this. It's a constantly evolving and iterating process where insights gained at one level may send you back into earlier stages as you try and make sense of the data, revise hypotheses, et cetera. So let's just look at one example of how this plays out in a real-world case. This is really focused on issues really in the intersection of visualization and modeling. And then throughout the talk, we'll slowly make our way kind of back up the stack, as it were, to look at issues of data in rawer and rawer states. So here's a data set. Let's go straight into a visualization. This is actually friendship networks extracted from Facebook. And if you're curious, yes, this is actually my personal Facebook network, circa from a couple years ago. And here we're using visualization to try and understand something of the patterns of connectivity within this network. So here the individual circles are nodes representing people, and then the gray edges are links, basically articulated friendships on Facebook. We then run a layout algorithm, which basically simulates a physics model in which nodes repel each other as charges and edges act as springs. And eventually the system settles into a state where we can start to see clustering patterns more effectively. In addition to that form of modeling, that layout, in addition, we've run some statistics. So in this case, each of the circles is sized by betweenness centrality, which is a network measure that gives us a sense of how central an actor is within the social network. So people sized larger here basically are hubs that are better connected or serve a central role within this network. And looking at this visualization, we can start to understand something that might inform subsequent modeling. So for example, we see one giant prominent cluster, and then we see some satellite clusters. These actually correspond to different groups in my life. So for example, those satellites are high school and undergraduate friends, where that giant cluster is people I met in graduate school or also work in the same profession as me, whether it's as a human-computer interaction researcher or out in industry. And for those of you who know a little bit about social network analysis, you may even recognize another pattern of that giant blob. That is, it has core periphery structure. That is, a denser core surrounded by a looser periphery. Very common in social networks and something that we're able to glean from this particular representation. But one of the themes of this talk is about data transformation, and that includes both transformation at the low level, but also transformations of how we represent data. This is just one visual representation, and there are others that we could consider for this type of data. So in this case, undirected networks. So in addition to a node link diagram, which is the representation shown here, we might show something else, such as an adjacency matrix or adjacency diagram, where now what we've done is taken the people and made them the rows and columns of this matrix, and then we fill in a cell, blue with a dot, if there's a link between them. And so on top of that representation, we also do some more analytics. So in this case, we perform statistical seriation, which is a fancy just way of saying that we try and permute the matrix to better show cluster structures. So in this case, we've reordered the rows and columns to try and place highly connected people near each other. And this gives us this sort of banding structure along the diagonal, which is showing us underlying clusters. And so one of the nice things about this view is it allows us to see something that was missing in this previous view. So here in the node link diagram, we have lots of clutter of all these overlapping edges. And by having good sorting and sort of an edge-forward representation, we can start to see substructure. So for example, in this big chunk in the center of the display, we're actually seeing that there are clusters within that giant group we saw earlier. And in fact, the top left cluster, as well as the two in the center here, are actually all members of that original blob. And we're actually able to see sub-communities. In this case, one corresponding to computer science students at Berkeley, one is corresponding to the Berkeley Information School, and another to researchers out in the field. And we can see to the degree to which they're connected, but we also get a sense of this structure. And at this point, we might be feeling pretty good about ourselves. We have a nice, initial qualitative understanding of our data. We might feel confident about it enough to begin doing subsequent modeling efforts. So for example, if I'm working at LinkedIn or Facebook, I might want to take data like this and use it as a source for then doing link prediction. Can I, for example, suggest new contacts or friends to you? But I would caution you from running too fast towards, more automated analytic techniques. So here we've looked at this data under two different representations, but each one of them only has a certain perspective on the data. What if we just take this matrix and try and look at the data in a more raw format? So instead of trying to use statistical measures to sort the rows and columns, let's just look at the data in the raw order it was returned by the Facebook API services. Once we do that, a very stark pattern emerges. So I'm sure many of you are noticing this big white square in the bottom right of the matrix. And so one thing that's important to know as you try to interpret this is that now what we're seeing is a matrix sorted by Facebook ID. So the rows and columns are just basically increasing identifiers. And for those of you who are unfamiliar, this identifier is basically just a counter that tells you when you joined the system. So basically in the upper, the left, we have people who joined Facebook a longer time ago, and then on the far right, the people who joined most recently. And so under that interpretation, it would seem that all of the brand new users to Facebook in this case had not friended each other. And while there may be some truth that new members may be less connected than older members, we also have reason to believe that new members come on and are actually quite active in growing their network. To have such a perfectly regular pattern would seem highly unlikely. And indeed, I saw this and thought there can't be something, there has to be something wrong with this data. And so it turns out, as I dug deeper, what I found was I had tried to be clever and write a single query to the Facebook API to get all the data at once, at which point it silently hit the 5,000 result limit, basically returning to me a very kind of underpopulated data set. So under normal operating circumstances, whether I don't look at the data and just begin to model it, or even using standard visualizations such as these, I actually miss the fact that up to 20% of the interesting data is missing because of some error in how I specified the query. And so this is just one of the many examples that come up in real-world data analysis, where here we may have gathered a data set and we're focused on visualization and modeling, but in the process of doing so, the visualization realizes that we have a severe data quality problem, that the models we make are probably going to be inaccurate given the missing data. So this kind of kicks us down to another part of the process. In this case, we have to re-engage in data acquisition and begin the cycle anew. And so the underlying lesson here is that given that this is the normal mode of operation with data analysis, how do we design tools to better support analysts in actually making sense of data? And there's some different ways we're approaching it. And so what I'd like to talk about next is also, how do we use visualization in particular as part of that process? And so one of the questions that I've asked in my research group and also in our work at Trifacta is, how do we best support expressive and effective visualization designs? So in this case, we're trying to take data and map it to visual properties of different shapes or geometries, position, size, shape, color, et cetera, to try and better reveal patterns using our well-evolved human visual systems. Often much easier to spot interesting patterns than if we were looking at raw data alone. But there's a wide space of visualizations. Creating them can be difficult, and finding the most effective ones can also be hard. So let's just look at some of examples of the types of expressive visualizations that have been developed. So one of the things that's fun about working in visualization has a really long history. And so this visualization here is actually centuries old. This was designed by the Scotsman William Playfair, who among other things is credited as the inventor of the pie chart, which is actually a relatively recent historical invention. This is one of the first economic dashboards, if you will. And so what you're seeing plotted simultaneously are the wages of a mechanic against the prices of wheat. So this is kind of the early days of capitalism, certainly the beginning of the Industrial Revolution, mercantilism, et cetera, is all happening. How does these new economies work? And will workers be priced out of their ability to sustain themselves is an important question. So here this data is sort of plotted against each other to see if they wax and wane in similar ways. And then just for context, we see along the top a third data set, which is the reigning monarch at the time, so you know who to either reward or blame depending on the current economic situation. And of course, this is the types of originally hand-drawn, the initial version of this was drafted. We want to be able to create these types of rich visualizations computationally. Another classic example is from the nurse Florence Nightingale, and what she did was collect statistics and then plot deaths of English soldiers in the Crimean War. This is a rather exotic display, and so it's using these area wedges to try and communicate time series. So these things basically move circularly across different months. And what you're seeing encoded as an area are the deaths, and the colors indicate red is battlefield deaths or deaths due to injury, black is other, and blue is deaths due to preventable disease. And so what this graphic was intended to show is that the major enemy of the English army was bad hygiene. And rather than show these numbers in tables, as her statistical colleagues suggested, Florence chose this strange representation on purpose to, in her words, affect through the eyes what we fail to convey to the public through their word-proof ears. And so while there are many visual representations we might consider instead, maybe bar charts, area charts, et cetera, that I would argue are more perceptually effective, Florence Nightingale chose to be evocative in this way to try and draw attention to an issue. So in some sense, this may actually be the first example of a modern infographic. Of course, no visualization tour would be complete without communicating what Edward Tufte argues perhaps the greatest statistical graphic ever created. This is Charles Menard's depiction of Napoleon's ill-fated march on Moscow. And so what you're seeing is the strength of the French army communicated as width over a geographical substrate, marching on Moscow and then returning decimated to sub-zero temperatures, which are communicated by this line chart underneath the map. So these are some classic examples of visualization. One of the greatest things about moving into the computational age is not just the ability to rapidly generate views, but also to interact with them. So a very simple example would be something like this. So here's plotting stock index such as the S&P 500. Using overview plus detail, we can get an overview in the bottom and then interactively zoom in on areas of interest to maybe explore them further. Another example would be to move into more dimensions. So this is a representation called the scatter plot matrix. And this is basically showing 4 dimensions of a data set simultaneously by showing all possible pairwise plots. Here are scatter plots. So we're going to understand how all these different variables relate to each other. But then we want to do operations as well. So for example, with brushing and linking, I drag out a region. So I highlight points in one plot, but then I automatically highlight all the corresponding plots in other charts as well. So that as I drag around, I might inspect how a cluster in one view does or doesn't project or hold up across the other dimensions of the data set. And the way we're doing this here, this is fairly simple because we're just highlighting single tuples. So we're really just highlighting points with the same primary key across these different charts. But you can also get much more complex brushing arrangements where you have different aggregation functions. So there's a really high query load that you have to sustain and be able to re-roll up the data based on the selections you're making here to support real-time interactive visualization. Another example is parallel coordinates. So this is a way of trying to show high-dimensional data as well. And in this case, we're showing 7 dimensions simultaneously. In this case, a data set of cars. So we have things such as the maker of the car, the cylinders, horsepower, weight, acceleration, et cetera. And how this technique works is we take, in this case, those 7 different columns, plot them on independent parallel axes, and then plot each tuple as a polyline that connects points across each of these axes. And while perhaps initially a bit intimidating, with some training, you begin to see some really interesting patterns, including, crossing lines tend to indicate inverse correlations. So you begin to understand something about the overall distribution of the data across multiple dimensions. And this is further augmented by interaction. So for example, if I drag here, through dynamic querying, I can filter the view, and in this case, select all the heaviest cars, see how they project across the other dimensions of the data set. And then by dragging around, I'm basically interactively rewriting the query clauses so that I can explore different subsets of the data. So for example, if I wanted to find all the cars that are fast, they go to 0 to 60 in a low amount of time, but are largely fuel efficient, so I might drag up here, I can begin to explore multiple objective criteria simultaneously in this interactive environment. And these are all examples of interactive visualizations using tabular data as the backing source. There are, of course, other data types that we really want to support. And so some examples include geographic data as well as networks. So here, for example, we see different airports in the US and the linkages between them as we mouse over. And to make this mousing quick, we actually computed a visualization underneath the scenes. So here's the Voronoi tessellation that allows us to select the nearest point, making it much easier, for example, to mouse over airports, what otherwise might be extremely small mouse targets. Here's another form of a network display, in this case visualizing source code. So each one of the nodes on the outer periphery of the circle is an individual source code file, and they're organized into packages. And then the graph links are showing dependencies amongst software modules. So as I mouse over individual elements, I can see which other pieces of code they depend on or which pieces of code depend on it. But in addition, what I've done is actually taken the package hierarchy and used that to route all of these spline edges. So I can actually see at a higher level how the different packages depend on each other, not just the individual classes. So for example, if I just drew straight line edges, I would get this view, which is much less informative than this routing by package hierarchy that lets me see large scale and individual trends simultaneously within the display. And then finally, we also want to be able to support transitions between different representations and transformations of our view of the data. So here's a rather gratuitous animation showing just the variety of ways you might explore something as simple as just 4 different stock time series data sets. While I don't actually recommend all of these views, it does give you a sense of the range of expressiveness that we might want to explore. And while some of them may be silly, I would argue that any suitably powerful language should also allow you to express at least a couple things that may be a little silly. So that's kind of tour of some visualization techniques. And so all the examples you just saw were actually built with a toolkit that we developed in my research lab, formerly at Stanford, called D3.js, or Data-Driven Documents. This is primarily the work of my former PhD student, Mike Bostock, who's now at the New York Times. So this is actually a domain-specific language implemented in JavaScript for writing these kinds of visualizations, so that you can build up interactive visualizations of your own for your data. And you may have seen some of these in the public already. So for example, back in 2012, when we were having the presidential election, this is one of the interactive graphics the Times ran that was built with D3. This one's showing a decision tree of how different candidates might win the election depending on how different states lie. And at the very bottom there in orange, you can actually see the various ways in which the Electoral College could have ended up in a tie between Obama and Romney. And of course, D3 has shown up not just in data analytic situations, but others as well. So here's an example from my colleagues at Stamen Design. This was sort of a surprise for us. We had built D3 really with the goal of supporting data analysts and scientists. What you're seeing here is visualizations of real-time Twitter tracking here used at the European MTV Music Video Awards. So again, while we set out to aid analysis, we sort of inadvertently provided the infrastructure for Lady Gaga's Twitter tracker. So these are some of the various types of ways we might explore use of visualization in both kind of fun public scenarios as well as data analysis. If you're interested in this is an open source project. You can go download it from GitHub, where last time I checked, it's the 4th most popular project on GitHub. So we're seeing a large uptake of D3. In fact, many of the vendors showing visualization software out on the floor today are using this software. And so that's great, but especially great if you like hacking in JavaScript. If you want to build custom bespoke visualizations and you like building in JavaScript, D3 is really the tool of choice. But we found that sort of setup, JavaScript hacking, with very customized visualizations, didn't always fit the bill. So part of what we've been doing at Trifacta is looking at ways of building higher level languages for visualization design. And so one of the open source packages we made available now is called Vega, which is basically a declarative grammar for visualizations represented in a JSON file format that then actually uses D3 underneath the hood to provide some of the visualization functionality. So to give you a sense of how this works, here's the basic idea in Vega is that visualizations can be viewed as compositions of simple geometric elements. So here's the actual graphical primitives that build up all the visualizations that you've seen so far today. So things like areas, rectangles, plotting symbols, raster images, lines, polygons, etc., form a small but extremely expressive lexicon of shapes that we can then determine the properties of these elements based on backing data. And so I won't go into all the details, but the basic idea, and we're inspired by other tools such as Wilkinson's Grammar of Graphics and the machinery underlying software projects such as Tableau, is an underlying grammar. So what's the right abstractions that allow you to build custom visualizations? That includes data models, data transformations that both work on the data, such as group by and statistical aggregation, as well as particularly visual transformations, such as layout algorithms and cartographic projections for geographic data. In addition, there's like libraries of scales that map data values to things like pixel positions, colors, shapes, etc., axes, legends, and then finally the marks I was just describing. And together, these abstractions provide a nice compositional framework in which you can build a large variety of visualizations. And so in this case, a simple pie chart might be defined as a JSON specification that includes all these elements I'm describing. So data definitions, scale definitions, and then mappings that determine the properties of marks, such as X and Y, angle, radius, fill color, etc., as properties of data. And so if you're interested in playing with this more, again, you can find it on GitHub. Some of the design goals that we sought to meet with this system are the following. So one is balancing rapid and expressive design. So by having a very simple componential model, you should hopefully build up expressive visualizations more quickly and with much less coding, but be able to get a huge design space of potential visualizations in that process. Second, we wanted to support reuse and sharing of visualization designs. So each one of these simple JSON specifications that I'm showing actually fully defines a reusable chart component in which you can actually plug in new data at any time. So you can build a visualization once, but then reuse it in new data sort of out of the box. Next, we wanted to support programmatic generation. Again, while I think D3 is an incredibly valuable and powerful tool, you have to write low-level JavaScript code. And we'd want to be able to support other programming environments to automatically generate visualizations. So by representing the visualization purely declaratively in JSON, you can now write programs that generate visualizations as output. It makes it much easier to do so because it's a computationally friendly format. And finally, by having this declarative layer, we're actually able to do add a lot of flexibility with respect to performance as well as the platforms that we're running on. So even a simple example is we can hit different rendering targets such as HTML5 Canvas or SVG from the same specification. In the future, that might grow to include things such as WebGL, so you can get higher performance graphics, all using the same specification language. And so if you're interested in playing with this more, it's online as Vega. There's actually an online editor, so if you are interested in going to play with it, I'll jump out of my slides and show it to you briefly. You can come in, here's the home page. There's a number of visualization examples already there. So for example, I might load in a choropleth map, in this case visualizing unemployment statistics by county. And then you can interactively edit the JSON specification here to get a sense of different visualizations you might build or explore different design options. And there's again an expressive range of visualizations you can create this way. For example, here's the scatter plot matrix I showed you earlier. We just saw maps. Another example would be a stacked graph, in this case showing 150 years of occupational data in the US. So here you see the farmers back in 1850, and you see how farming as a percentage of the labor force has fallen over time. And similarly, you can explore other professions in that way. And then, of course, no visualization library would complete, as I said, if we don't also include the ability to reconstruct Napoleon's march. So that's here too as well. So yeah, play with it if this is useful to you. We'd love to get your feedback as well. This is still being actively maintained. Has a lot of support for visual encoding, and we're exploring some really exciting ideas in the lab right now about declarative design of interactions. So how do you do interactive design instead of callback hell? Building out principled streaming workflows to define interactivity is something that we're actively exploring. So those are some of the challenges and opportunities that we've been identifying in visualization. And we want to make it really easy to explore lots of different representations of data, and hopefully they'll make the data more accessible and useful to a broader audience of people. But of course, all of that is for naught if we can't get the data prepared for visualization and modeling in the first place. And so these issues of data cleaning and integration and how we can make those more interactive are also a central challenge. And I'd actually argue even perhaps a deeper and more important challenge facing the data science community today. So for example, my co-founders, Joe Hellerstein and Sean Kendall, and I ran out and did a large set of interview studies to try and get a sense of what is the day-to-day life of practicing data scientists. And again, we kept seeing quotes like this. I spend more than half of my time integrating, cleansing, and transforming data without doing any actual analysis. Most of the time, I'm lucky if I can do any analysis at all. And in fact, across most of our quotes, this was something of a lower bound, and that most people said something around 80% of their working day was actually like importing data, cleaning it up, integrating it with other data sets, and then the leftover 20% might be for fitting a model or maybe generating some visualizations. So it seems like a lot of effort lost in getting these data sets ready. And moreover, the technical skills required to get it ready are preventing many other people from participating and prepping data for their own analytic tasks. So especially in a BI context, how can we provide better self-service access to data sets, particularly those that haven't yet been cleaned and structured and sort of blessed to be included in the data warehouse? And so I see this as something of the elephant in the room of data analysis work. This is what we're spending the majority of our time doing, but maybe not putting enough effort into fully addressing. And so this is the core problem that we're trying to tackle at Trifacta. Is that how can we take the job of data preparation, data transformation in particular, and make it faster, easier, and more accessible? And so let me jump right into a demo for how we try and do that. We're building interactive systems to really replace the need for custom programming. So consider a data set like this. This is actually call detail records. So imagine you work for a telephone company. You want to understand the performance of your network. You might also want to understand customer retention and loyalty and how that might relate to performance of your network. So you'd be looking at data like this, which is just basically a log of all of the calls or activities made from mobile phones. And this is a computer-generated, and collected, data file, but still something that you can't just, easily load into a database or a statistics or visualization package and get up and running. So let's look at how we might get this data ready in a tool like Trifacta. So here we have some different projects in Trifacta. We've loaded some data sets, and let's go ahead and look at CDR. That's the call data record data. So here we can see we uploaded a text file. It's sitting here on HDFS now, and it's over 100 megabytes in this case. So not huge data, but still, not a tiny CSV either. We can go ahead and start transforming it. So this will pull the data into the transformer workspace provided by Trifacta. And so now you see a data table view here, kind of familiar, similar to spreadsheet UIs along the bottom. A transformation editor for authoring new transformations that we'll see in action shortly. And then on the right, a script, which shows all the operations that have been performed on the data so far. And what you'll see is that Trifacta has automatically suggested and executed 2 transformations on a sample of data. So the first thing you know is our original data set was over 100 megabytes. Right now we've pulled the first n bytes, in this case a 500 kilobyte sample, and pulled it into the viewer. And then we can determine how to break up the records. So we automatically inferred to split into rows based on a carriage return, and then to columns based on tab. And if we disagree with that, that's fine. We can, of course, just undo and then see the data in a more raw state. But in this case, we're pretty happy with the suggestions that have been made. And at this point, once we've broken the records, we actually automatically spin up a job to then understand the record breaks in the larger data set. So if we wanted to, we could actually, instead of our top n sample, pull in a truly random sample of the data set for perhaps more accurate statistical analysis later. But we'll forgo that for the time being. Because what we need to do now is still further structure the data. One issue is that many fields remain to be delimited. So for example, we see slashes are used across these different fields. For example, IMSI is a subscriber ID. That's the person using the phone. The IMEI is the device ID, so that's the actual phone ID. We like to break these out into their own columns. So in this case, I'll just select the slash because that's what I'm interested in. And that's used as evidence for Trifacta to then try and guess what I'm trying to do. So based on both the contents of the data table and the selection I made, Trifacta searches over a space of possible transformations and then returns them back to me as suggestions. And as you might see in the transform editor here, the top ranked suggestion is to split column 2 based on that slash character. And then next to the original column, I see visualized a preview, which visually shows me what the effect of running that transformation would be. And indeed, this looks good, so I can just go ahead and hit enter and then add my transformation to this growing script here. And I might notice something else. For example, this field has a lingering angle bracket, so I can just go ahead and select that. And again, based on the text and the context, for example, it occurs in the end of this cell, I actually get a different suggestion, which is here to just clean it up by removing that character because I no longer need it. So this is a replace transform replacing with the empty string. So I can execute that, and now I've cleaned up that column a bit more. And I can continue in this way to break up additional fields. So for example, here I have date, time, as well as call duration. So that's a simple split based on the slash. Similarly, I have pipe delimiters in this field over here. Very strange heterogeneous mix of delimiters in this particular format. So I can go ahead and then I can split that as well. And so in this way, I can begin to split out my data and get better defined columns. Now, as I'm doing this, you're probably noticing a number of other things that are happening. I'm automatically trying to infer data types for each column. So you might see things like this is a string column, this is inferred as a numerical column. Based on those data types, I'm generating summary visualizations, such as numeric histograms or categorical histograms that are sorted to show you top-end values, as well as doing some initial data quality analysis. So for example, for these columns, the identifiers, which are numbers, we inferred a numerical type, but we see that we have an anomaly, that there's a non-number in this row. So if I click that, I can say, highlight for me where the anomalous values occur. In this case, it's rather simple. It's the header row, which is still part of the main data table. So I can just click that row, get the suggestion to make it the header, and then go ahead and update the data in that way. I can further also modify the suggestions that Trifacta is making. So for example, I might want to treat the user ID as a unique kind of key value, not an integer. So I can change that data type to treat it sort of as a string or a categorical variable. And now instead, you can see I get a histogram of the users who've made the most calls. So I can do this. I can do a number of different operations. One thing I might do is say I want to break out these, this date time information in this column. Let me see if I can't increase the column width here. So there's various ways I can do that. I could split on T, or in some cases I need to learn more complicated patterns. So for example, if I select the text 849.19, it suggests an extract procedure. In this case, find all instances of that exact match, which for many text analysis tasks, basically a count if, can be extremely useful. But in this case, I actually don't want that. I actually want to get all times. So I give it another example from which it can generalize. So given these examples, you can now see I'm going to extract text that match an inferred pattern. We've actually learned that I'm looking for numbers separated by colons. So it's actually learning on the fly, in this case, how time is represented, which is useful for things for which you don't have a predefined data type. And breaking this out, I can see in the preview that indeed Trifacta successfully identifies this as a time field once I separate it in that way. But let's go ahead and reject that for now. We don't need to look at times further. There are other things that might be of interest to us, including, for example, the large number of missing values here. Right? This is actually a drop code. So we look at this column. It's actually reasons for disconnecting. And then there's many, many empty values in this column. So we might ask why. So if we select that, we actually get recommendations, we show where are all the null values residing. And we can see, for example, if we go over to this column, which is actually showing us the call type, all of the null values correspond to SMS text messages. And this makes sense because SMS text messages don't disconnect, so there's really no legal value to have. So I could just go ahead and delete that data since I don't really need to look at it anymore. I can then continue on to do all sorts of analyses with this data. Let me go ahead and delete those values. So for example, I might want to focus on some particular columns of interest, so then I can just go in, find the columns I don't need, select those, and then I can just simply drop those. So I can do multi-column operations at once. And then I can maybe focus squarely on, okay, given a set of users, and I know the length of their call, why are they disconnecting? Well, these disconnect codes are really opaque. So there's like 11 and 19 as values, but what do they mean? Well, this is where I'm going to want to do a join. So in this case, do I have actually a lookup table that will give me a more human-readable version of this data? So doing that, I might go in and then actually do a lookup table. And fortunately, I've already uploaded a different data set which provides a lookup table for the drop codes. So I select that. And then I can look at the different fields, such as the code or the description. I'm going to want to do the lookup based on the code. Do that, and I can just automatically extend my data set with new values, in this case, ones that let me better understand the nature of the call. So I no longer need this column, so I might hide that. And now I might export this data and do some analytics on it, or I might want to do a roll-up to better understand it at a per-user level, because right now we're looking at records for every single call. So for example, I could aggregate, and in this case, I might want to do is say, well, let me look at the count of calls, as well as also the average duration for calls. And then doing that, I will group that by both the user ID as well as the description for why the call was dropped. So I do that, and I can get a preview as well. I can go ahead and execute it. And now I have an aggregate over my data that I could also export. But I can even do further calculations if I want. So just as one final example here, I can actually compute a dropped call percentage, where I use a value transform, really just to author an expression where I can take my count, divide it by the sum of all counts if I group by the user ID. So doing that, I can compute percentages. So I'm actually mixing both row level and table level aggregates within a single calculation. Doing that, I add that, and now for all the things that are call ended, I see the successful call completion rate. For those marked call drop, I see the percentage of all calls for that user that were dropped. And this could be a really useful data set now for joining against my customer database record. So does the percentage of dropped calls in any way correlate with whether or not people have stayed loyal customers or if they've left the service? So in this way, I've prepped my data from something messy to something structured that I can now use in downstream analytics. In addition, in doing this, I've not only done transformations of data, the real output has actually been this script. So I've actually built up a program. And so what I can do is, for example, now I can say run job. Instead of operating on this sample, I can take the transformations, compile them into pig scripts, for example, and run them at scale at a Hadoop cluster. So for small data, I could choose to run these transforms locally. In this case, we're compiling it to a JavaScript-based data flow language. Or we can run in Hadoop, where again, we're taking our data flow specification and turning that into pig scripts. So in this case, I'll just go ahead and click run locally since it's not that big. And then it will take me to a page where I can actually monitor my running transformations or reuse transformations as data sets update or as new data sets come in. In this case, my job's running, and it will finish in just about a minute. But in the meantime, let's look at the results of a previous run, since that'll be quicker. We can, of course, export the results, so we can get access to the data. It can be logged into HCatalog, so other tools can pick it up. Or I can see the results of the job. As a result of running these transformations, we also collect a lot of statistics. So what if there are anomalous data records in the larger data set that we're missing from our sample? We're going to want to be able to catch those to improve our transformations and pull better samples. In this case, we can see that we ran the job without issue, that it completed, and then all of the data values showed up valid. And we've computed histograms so we can actually see the distribution of these values across the entirety of the data set that may be residing in our cluster. So in this way, the key insight is to try and take interaction with the data, but translate that into scalable programs that we can run over very large data sets that reside in our Hadoop clusters. So this is sort of like the general approach of Trifacta. So coming back to give you just some quick recap on what you saw, one of the things that we're exploring in this tool is this notion of what we call predictive interaction, is that rather than directly writing code for things, you have visual representations which you can interact, and from which the system can then try and infer your intent. So in this case, we take selections and we look at the context of the data, search over a space of transformations, rank them, and then provide them back as recommendations. We then close the loop by then visualizing those transformations themselves, providing visual previews to help you rapidly decide if the operation is the one you want to perform. So in that way, really trying to use a visual channel to both write and then assess programmatic statements. And then putting that all together is this model for predictive interaction. And then again, the resulting output is not just transformed data, but an actual script. And this is realized in a high-level domain-specific language that we call Wrangle. And we can compile this to various platforms. So for example, for scalability in Hadoop, we compile it to pig scripts. And this allows us to run transformations at scale, and we're kind of a faithful player within the Hadoop environment. We're both HTTP and CDH certified, Yarn ready. We'll plug in and make data sets available through HCatalog and also speak to kind of the standard Hadoop file formats. So really trying to help you take messy data and make it much more actionable in analytic workflows. So those are just some of the examples of the challenges I see by looking at the data lifecycle in this more complete fashion. So what are the challenges that users actually face in getting into actionable insights, whether it's through modeling, visualization, data preparation? how do we build better interfaces to allow us to do this more effectively? And again, as we saw in Trifacta, what are some of the implications for how we then interface and develop large-scale data processing systems? And I think there are many, many challenges to consider as we think up and down the stack here. And I think we'll all be occupied for many years to come in challenges that arise in user interface design, system design, as well as machine learning. So I think the future is bright, but there remains a lot to do. So with that, I'd like to thank you for your time. And if you have any questions, I'd be happy to answer them in the time that we have left. So thank you very much. Yeah. So great question. It was basically how do we operate on semi-structured data where you might have nested record? So right now, our primary focus is on what I like to call should-be structured data, like data that should reside in a table, but for whatever reason doesn't. And that can include multi-line records and all sorts of really complicated things. And you mentioned healthcare, and in fact, most of our early customer engagements are people doing healthcare claims and records processing, where you have a mix of structured records and text. So a lot of things we're doing is actually extracting patterns for important notes in text as well. Right now, we do support some amount, or building support for hierarchical file formats, but usually that would be things like JSON, Avro, XML that are actually flat, even though they're within a hierarchical format. And then we're not there in the product yet, but we're currently exploring ways to look at how to better support more nested structures. And as you know, there's a variety of things where you can flatten them into tables or multiple tables, or try and deal with kind of document-style data directly. And so it's an important challenge, but it's on our roadmap for the future. Cool. Thanks. So I think we're out of time. If you have any more questions, come see us at our booth. We'll be happy to show you more and answer any questions you might have. Thanks.